Good afternoon. Today we'll be starting a new chapter, chapter 7, dealing with atomic structure. Atomic structure deals with energy, wavelength, what else? Wave particle duality, and quantum numbers. This is a particularly short chapter, so we'll be going through it quite quickly. This chapter will only have 2 lectures. The first one dealing with energy and wavelength, and the second one dealing with quantum numbers. So sit back, relax, and enjoy the show. Okay, so again, today we're starting atomic structure. And atomic structure deals with, in particularly, how electrons behave in the atom. So we'll be talking about wavelength, energy, photons, quantum numbers. So all of this is based on how the electron behaves in the atom. Oops. So first we're going to talk about what's called electromagnetic radiation. Electromagnetic radiation is the oscillation of electric and magnetic forces. And these forces are perpendicular to one another. So any type of energy or electromagnetic radiation is energy that has electric and magnetic fields. And so these magnetic fields oscillate and you get electromagnetic radiation. And this energy is transmitted in the form of waves. And we'll talk about what some wave properties are in just a moment. But the electromagnetic spectrum is a very broad spectrum of energy. For some reason I still can't draw straight. And so on one end of the electromagnetic spectrum, you have very short wavelengths. On the other end, you have very long wavelengths. So in between, you have all these different sorts of electromagnetic radiation. So cosmic rays have very short wavelengths. So on the order of picometers. Then we have gamma rays, X-rays, UV rays, which is produced by the sun. Then we have the tiny sliver of rays, as it's called, visible light. And so visible light goes anywhere from about 400 nanometers to 700 nanometers. So UV is shorter than visible and IR is longer than visible. And then we have infrared, microwaves, of course, radar, radio, and TV waves. So these are very long wavelength forms of electromagnetic radiation. The shorter the wavelength, the more potent the rays are be, meaning they have more energy associated with it. In addition to wavelength, another property that we'll see in just a moment is the shorter the wavelength, the higher the frequency, the number of times it goes up and down in a given unit of time. The longer the wavelength, the shorter the bigger the smaller the frequency, because there's less of the ups and downs in one unit of time. So for wavelength and frequency, they're inversely related to one another. So here we have small wavelength and high frequency on this end. On this end, we have long wavelength and low frequency. So TV rays, radio waves, they're not very energetic waves. Very low frequency, that's why they don't cause much disruption. Now moving on, talking more about the wave properties of electromagnetic radiation, and visible light, which is the small slivers of electromagnetic spectrum from is a small sliver of electromagnetic radiation from about 400 to 700 nanometers. It has some wave-like properties. So what are wave-like properties? Well, we just introduced them in the last slide, and these are wavelength, which is the Greek symbol lowercase lambda, and it's the distance between peak and peak on the wave, or trough and trough. So it's the distance between the peaks on a wave or the troughs or valleys on a wave. Amplitude is the height of the wave or the depth, the height of the peak or the depth of the valley. In chemistry, we don't use amplitude that much. We mainly use wavelength, and the other one is frequency, which is the Greek symbol lowercase nu, and it's the number of cycles, the number of up and downs, the wave, number of peaks and troughs the wave goes through in a given unit of time. And typically, frequency is given in second inverse, or commonly referred to as hertz. Now, in physics, if you know the frequency of a wave and you know the wavelength of a wave, you can calculate its speed. But for electromagnetic radiation in a vacuum, they all travel the same speed, which is 2.998 times 10 to the 8th meters per second. And this is referred to as the speed of light. Again, this is the fastest electromagnetic radiation can travel in a vacuum. And it's a constant in a vacuum. So since the speed is constant, if we know the wavelength, we can calculate the frequency. If we know the frequency, we can calculate the wavelength. So here we have this equation here that relates frequency and wavelength. So what we know is frequency is inversely related to the wavelength. And by the way, wavelength in chemistry is usually given in such units as nanometers, picometers, or sometimes angstroms. These are the three common types of wavelengths in chemistry that we use to describe electromagnetic radiation: nanometer, picometer, and angstroms. But you have to remember that the speed of light is in meters. So anytime you use this equation, you got to convert the wavelength into meters. That's a very common mistake that students forget, to convert the wavelength into meters. So now back over here, we see that frequency is inversely related to the wavelength. So what this means is you have higher frequency, you have shorter wavelengths. When you have lower frequency, you have longer wavelengths. So they're inverse to one another. High frequency is short wavelength, low frequency is long wavelengths. So this is the relationship between frequency and wavelength. So here we want to know which one of the forms of electromagnetic radiation has the highest frequency. So what we're looking for here is the highest frequency. And so highest frequency, high frequency, we have short wavelength. And so in order to answer this, we need to determine which one of the forms of electromagnetic radiation have the shortest wavelength. So let's go through and see. So red light, well, red light's over here at 700 nanometers. Radio waves is over here at 10 meter or 1 meter range. So obviously red light, which is at 700 nanometers, shown down here, is shorter than radio. So we can go ahead and omit radio waves because its wavelength is in the range of meters, whereas red is in the range of 700 nanometers. Next we go to C. C is cosmic rays. Cosmic rays is over here, and its wavelength is picometers. And picometers are smaller than nanometers, so we can disregard red light. Now UV rays are between nanometer and 1,000 nanometers, which is still bigger than cosmic rays. So again, UV is right here. Cosmic is over here to the right, or to the left, sorry. And so cosmic is still still higher frequency than UV. Blue light is around 400 to 500 nanometers. So again, 500 nanometers is bigger than a picometer. And then lastly, we have broadcast bands, which are on the range of fortitude of a kilometer, which is a lot larger than a picometer. And so the correct answer in this is cosmic rays. It has the highest frequency, aka shortest wavelength. Now broadcast bands would have the lowest frequency out of the ones stated here. Now let's look at another example. So here we want to know what's the wavelength in nanometers of light with a frequency of 5.8 times 10 to the 14th hertz. So again, what we should remember is that frequency and wavelength are inverse to one another. So since this is a very large frequency, you can imagine that the wavelength would be very small. So 10 to the 14th is a very large number. So the wavelength is going to be a very small number. So what we need to use is this equation where we solve for lambda. So lambda is wavelength. C is the speed of light, which is a constant. It's always 2.998 times 10 to the 8th meters per second. It can also be written sometimes as 3.0 e to the 8th meters per second. Either one is fine to use. You're going to get the same answer, roughly, within a margin of error. And then nu is frequency. So we take the speed of light, we divide it by the frequency, we get the lambda. Now best to use parentheses when you're doing these operations because the calculator goes by order of operations. So we put in the speed of light, we put in the frequency, we get the wavelength in meters. But it wants the wavelength in nanometers. So we got to convert meters into nanometers. So remember, there's 10 to the 9th nanometers in 1 meter. So you got to multiply by 10 to the 9th to convert the meters into nanometers. And we get 516 nanometers. I mean, depending on the rounding, if you're within plus or minus 1 of that, that's fine. 515 to 517, no problem. And so that's going to be the color of light around blue to light blue color. Be right about here. Again, the main thing is to make sure you use parentheses when you put it into the calculator. So that was the wave properties of light or electromagnetic radiation. Again, wave properties, it has frequency, it has amplitude, it has wavelength. Now, it was discovered back, in the early 20th century that Einstein, or it wasn't discovered, it was proposed that Einstein thought that light was actually a stream of particles and that these particles were called photons. So whenever light was emitted, it had a stream of particles within that light beam that were called photons. And there was an equation that was developed to calculate the energy of a photon. So the energy of one photon is a constant called Planck's constant. It's 6.626 times 10 negative 34. It should be joules second. So it's the smallest packet of energy that can be transferred times the frequency. So you see here, frequency and energy of a photon are directly related. So the higher the frequency, the more the energetic the photon is. So things like cosmic rays are very energetic. That's why they cause very deadly consequences. And so if we take the equation from the previous slides involving wavelength and frequency, we can see the relationship between wavelength and energy. So frequency is C over lambda. So energy of a photon is inversely related to its wavelength. So the shorter the wavelength, the higher the higher energy photon you have. And if you want to know the energy of a mole of photons, you just take the energy of one photon and multiply by Avogadro's number. And that's how you get the energy of a mole of photons. So now let's look at a practice problem. Here we want to calculate the wavelength in nanometers of a photon that possesses 8.19 times 10 to the negative 18th joules of energy. So we're going to need two equations. We're going to need the equation for wavelength so that we can calculate the wavelength of the photon. And we're going to need the equation for energy of a photon, which is E equals h nu. And we're going to be using two constants, the speed of light and Planck's constant. So then what we're going to do is we're going to combine these two equations and get a relationship between energy and lambda. Again, energy and wavelength are inversely related to one another. So if you notice here, the energy is very small, on the order of 10 to the negative 18. So that means the wavelength is going to be very large. So again, we have our speed of light. We have our Planck's constant. We rearrange this to solve for lambda. So it's hc divided by energy of the photon. And we get this expression. Again, make sure you use parentheses. The most common mistake that is made is students don't use parentheses and they get some wild number like 10 to the 90th or 10 to the negative 70. 10 to the negative 70 is like 69 zeros and then a 1. It's basically 0. So make sure you use parentheses when putting this in the calculator. Now we get the wavelength is in meters. We convert it to nanometers. So here the wavelength is in meters. We multiply by 10 to the 9th to get the number of nanometers that this photon has. And so this photon has a wavelength of about 24.3 nanometers, which puts it somewhere near the UV region of the ultra or electromagnetic spectrum. So this is somewhere approximately a UV photon, because 24 is in the near, it's around the UV region of the electromagnetic spectrum. So this is how you calculate the wavelength of a photon given its energy. So this is the energy of one photon. So next here we're dealing with a different type of problem. We're saying we're describing a person was exposed to a beam of electromagnetic radiation. This radiation exhibited 325 kilojoules per mole of photons. What is the wavelength? So here we have this beam which contains numerous photons. The beam has a energy of 325 kilojoules per mole. What's its wavelength? So these are the equations we're going to be using. We're going to be using the lambda equation, C over nu. We're going to be using the energy of a photon, H times nu. And since we're dealing with a mole of photons, we're going to be using Avogadro's number. So when you have a problem like this, step number one, find the energy of one photon, because this is the energy of a mole of photons. And so to find the energy of a photon, it's equal to the energy of a mole of photons times Avogadro's number. So if you know Avogadro's number, you know what's the energy of a mole of photons, you can find the energy of one photon. So that would be energy of a photon would be, now here notice I made a, oh, that's fine. Yeah, sure. 325 kilojoules per mole. Oops, I made a boo-boo. Let's see, it should be divided by, no. Oh yes, it should be divided by Avogadro's number. So this should be divided by 6.022 times 10 to the 23rd photons per mole. So I made a little error on that. You actually have to divide by the Avogadro's number, not multiply. So when we put that in, the energy of a photon is 5.397 times 10 to the negative 22. 5.397 e to the negative 22 kilojoules per photon. So that's the energy of one photon. Now remember that Planck's constant is joule per photon. So we got to convert this to joules by multiplying by 1,000. So it'd be 5.397 e to the negative 19. And this is joule per photon. So that's the energy of one photon in this beam. And again, the reason we need joules is because Planck's constant is in joules. So that's why we had to convert the kilojoules into joules. That's step one. So we found the energy of one photon. Step two is we got to find the wavelength. Remember, wavelength, I don't have the symbol for lambda, but lambda would equal hc divided by the energy of a photon. So if we know h and c, which is Planck's constant, and speed of light, we know the energy of a single photon, we can calculate the wavelength. So wavelength equals, so lambda equals all of this divided by energy of a photon. Now, the reason I use all these parentheses is because this is how many parentheses you should use when you're calculating the lambda in the calculator. So here, lambda equals, let me work this out. You get about 3.68 e to the negative 7 meters. So notice this is in meters. We want the answer in nanometers. Let me just double check, make sure everything is right. Yep. Now we need to convert this to nanometers. So lambda this equals 368 nanometers. So that's the wavelength of one photon in that beam. All right. Give you a second to look at this before we clear it. Look at one more example. So here we have gamma radiation, which is used sometimes in cancer treatment. It says a gamma ray photon has a wavelength of 20,000, that's femtometers. What is the energy for a mole of these photons? So here we have a wavelength of a photon that's in femtometers. It's 20,000 femtometers. We want to know what's the energy for a mole of these photons. So again, we're going to be using these equations. And since we're dealing with a mole of photons, we want to know the energy of a mole of photons. We have to use Avogadro's number. Per mole. So the first step is we need to take the wavelength and convert it into meters. So step number one, convert wavelength into meters. So how we're going to do this? So we have 2e to the fourth femtometers times 1 meter is 1 to the 10 to the 15 femtometers. So this means we have 2e to the negative 11 meters. So that's the wavelength of this photon in meters. Again, since you're dividing, you subtract exponents, we get 2 to the negative 11. So that's the first step. Second step is to determine the energy of a photon. So energy of a photon, we'll say E of P equals, let's write photon, equals hc divided by lambda. So this is going to be the energy of one photon. So E of photon, oops. So again, since this was a very small wavelength, it should be a very large energy. So we get that the energy of one photon is 9.932 e to the negative 15 joules. That's the energy of one photon. But if we notice here, it says what's the energy in kilojoules for a mole of photon. So the next step, we're going to convert this to kilojoules. I'm going to divide by 1,000. So when you divide, you subtract exponents, so this will be 9.932 2e to the negative 18 kilojoules. So that's the energy in kilojoules. Third step, determine the energy for a mole of photon. So the energy of a mole of photons is equal to the energy of a photon times Avogadro's number. So energy equals 9.932 e to the negative 18 times e to the 23rd. And we get about 5.98 10 to the 5th kilojoules. It's about 598,000 kilojoules. It's a very intense beam. And so that's the answer in kilojoules. While you're looking at this, I'm just going to double check all my work. Yep, and that is correct. So now moving on, talking about more how these electrons or how light is associated with elements. Sir Isaac Newton first discovered that various colors of sunlight can recombine into white light. So white light contains all the colors of the rainbow. And so that's referred to as a continuous spectrum. You see all the colors of the rainbow in the light. But elements and atoms are a little bit different. Elements and atoms only emit not a continuous spectrum, but very discrete spectrum. So very discrete wavelengths of light are emitted when an electron in an atom moves, and that's referred to as an emission spectrum. And so every element has its own unique emission spectrum, which is called an atomic line spectrum, because every element has a different number of electrons, and those behave differently in different atoms. And so these spectral lines only occur at specific wavelengths. And so every element has its own unique atomic line spectra for it. So you see hydrogen emits a red photon, a green photon, a blue photon, and 2 violet photons. And remember, hydrogen only has 1 electron, so this is the 1 electron moving around. Helium, a red photon, a yellow photon, 2 greens, and 2 blues. So helium has 2 electrons. Again, this is how the electrons move in the elements. So every element has its own unique atomic spectrum. Now sodium only emits yellow electrons. So when you excite a sodium atom, when the electrons move, they produce yellow light. And that's how some of the stoplights have yellow, as they use a sodium filament in the light bulb. So you can actually identify elements based on the atomic line spectrum or spectra. And so based on how electrons behave in elements, there was a model derived to explain the behavior of electrons, or the behavior of the electron in the hydrogen atom. Because it's easy for a hydrogen atom, again, hydrogen atom only has one electron. So this is referred to as the Bohr postulates of the hydrogen atom, or the Bohr model of the hydrogen atom. So first off, he said energies are quantized. So what does quantized mean? Quantized, it's a fixed amount. So for example, when a chicken lays an egg, it's a quantized amount. You get one egg. You don't get half an egg or a quarter egg or a tenth of an egg. You get one egg. That's a quantized amount. Or if you go to the soda machine and buy a soda, you get a quantized amount. You get a can of soda. You don't get a half a can, a third of a can, etc. So energies of electrons are the same ways. They're quantized. So there's certain amounts of energy for that particular electron. Now, secondly, electrons, when they're in orbit, lack of a better term, do not radiate energy. It means they don't get off energy when they're just at a particular level or orbit. So for example, when you heat the stove and you turn it off, as the stove is turned off, the stove element continues to radiate heat. But for an electron, if an electron was at a particular energy level, it wouldn't radiate any energy. It would just stay until it moves to different orbits. That's when energy is transferred. Either it absorbs energy or emits energy. And so when it moves from a higher orbit to a lower orbit, this gives up a quanta of energy, meaning it releases energy. So as it goes from a higher orbit to a lower orbit, it releases energy. And these orbits are actually called energy levels. So as an electron moves between energy levels, if it goes from a higher energy level to a lower energy level, it emits energy. And we can actually calculate the energy for a particular energy level by using this equation here. So the energy of an energy level is equal to some constant times 1 over the energy level. And N is the energy level. It starts from 1, 2, 3, all the way to infinity. It can only be an integer. So you can't have energy level 1.5. It has to be 1, 2, 3, all the way up to infinity. So N is the energy level, R is the Rydberg constant, and it's shown here. 2.18 times 10 negative 18 joules. Now the Rydberg constant has different forms based on what the unit is. So here the unit of Rydberg constant is joules. Again, N is a positive integer. It's the energy level. So when N equals 1, we say the electron's in its ground state. Remember, hydrogen only has one electron, which is commonly found in the ground state energy level. When it goes beyond N equal 1, it's referred to as an excited state. So to go from the ground state to the excited state, you have to absorb energy. To go from an excited state to a ground state, you will release energy. And if this energy is it has a photon with a wavelength in the visible spectrum, you'll see that color photon up here. So this is an example of a Bohr model of a hydrogen. Again, the hydrogen has only one electron. And again, this model works for hydrogen and hydrogen-like species. So what's a hydrogen-like species? These are things that have one electron. So helium plus, lithium 2 plus, beryllium 3 plus, etc. So species with 1 electrons are hydrogen-like species, because hydrogen atom only has 1 electron. So those species with 1 electrons behave the same way. So again, when you're at the lower energy level, say n equal 2, you absorb a photon, you go up to an excited energy level. Now when the electron's at an excited energy level, again, while it's on the energy level, it does not radiate energy, but then it cascades back down to energy level 1. It emits a photon of energy, and this photon is in the visible spectrum. You'll see it as a color of light. So again, the further away the electron descends back to, or the greater in difference between the energy levels, the more energy that photon will have when it's emitted. So again, the greater the difference in energy levels, the more energy the photon, the shorter the wavelength. So the closer together the energy levels, the smaller the energy of the photon, the longer the wavelength. And so this led for 2 scientists, Johann Balmer and Rydberg, to develop a formula to calculate all the wavelengths of the electron and the hydrogen atom. This was based on empirical evidence. So they did the experiment and they developed an equation to calculate these wavelengths. This is referred to as the Rydberg equation. So 1 over lambda is equal to a Rydberg constant times the inverse of the difference in the energy level. So you do 1 over n1 squared minus 1 over n2 squared. Note that n1 is always less than n2 so that you don't get a negative number. Here the Rydberg constant's a little bit different. It's in meters inverse. So when you plug in n1 and n2, you can calculate the 1 over lambda, then you flip it, you get the wavelength for that transition. So let's look here. We have a few things. So the Balmer series, we do that a little bit better. The Balmer series are transitions in the visible spectrum. And for the Balmer series, all the transitions end in n equal 2. So again, the greater the energy level, difference in energy levels, the greater the energy, the shorter the wavelength. So from n equals 6, which is out here, n equals 6, n equals 6 to n equal 2 has a wavelength of 410 nanometers, whereas n equal 5 to n equal 2 is 434. So you see, the smaller the energy level difference, the longer the wavelength. And so both of these are violet photons. Then n equal 4 to n equal 2 is a blue-green photon with a wavelength of 486. So again, the smaller the difference in energy levels, the greater the wavelength. And then the last one, n equal 3 to n equal 2 is a red photon. So for Balmer series, the final state is n equal 2. So anytime you have a Balmer series transition, it always ends up at the second energy level. Now Lyman series follows the same rules, except Lyman series ends at n equal 1. So for Lyman series, final state is n equal 1. And notice for the Lyman series, it's in the UV region. So remember, UV is shorter wavelength than Balmer. So all of the, now make this note, all of the Lyman series transitions, which end up at n equal 1, have a shorter wavelength than all of the Balmer series transitions, which are in the visible spectrum. And then lastly, when all the transitions end at n equal 3, it's referred to as the Paschen series. And these are the three main series for the hydrogen atom electronic transitions. So again, the greater the difference in the energy levels, the shorter the wavelength. And since this is n equal 3, you see this is the infrared region. So again, the infrared region is the longest series of wavelengths in these three series. And so for Balmer, they all end in the final state of n equal 3. Excuse me, Paschen. So again, the shortest wavelength series is Lyman, and ends in n equal 1, then Balmer, which ends in n equal 2, and then Paschen is the longest, which ends in n equal 3. So this is just a different display of the three different series. And what you should notice is all of the Lyman series transitions have the shortest wavelength, then Balmer, then Paschen. But what you should notice in each individual series, so let's say we're just looking at the Balmer series. So in the Balmer series, the smaller the difference in energy levels, the longer the wavelength. The larger the difference in energy levels, the shorter the wavelength. So greater difference in energy level, shorter wavelength. Smaller difference in energy level, longer wavelength. And again, for Lyman series, you end in n equal 1. Balmer series, end in n equal 2. Paschen series, end in n equal 3. And so if you're transitioning between the different energy levels, you can actually calculate the energy associated with it by using this equation here. So this is again the Rydberg constant in joules, 1 over the energy level, the final energy level squared, minus 1 over the initial energy level squared. And if the initial level is greater than the final level, a photon is emitted, meaning it releases energy. When the initial level is less than the final level, a photon is absorbed. So there's lots of different equations to use to calculate different properties of these transitions. So here we have an example problem involving the hydrogen electronic transitions. So here we have a hydrogen atom with an electron in the n equals 6 energy level. So it's in the n equals 6 energy level, emits a photon of IR light. Calculate the change in energy of the atom, or should be photon, and the wavelength of the photon. So we want to calculate the energy of the photon. This should be photon, not atom. Oh no, we can do atom, fine. Yeah, change the energy of the atom. And the wavelength, and notice here it's in the wavelength in angstroms of the photon. So this is the equation we're going to use. So we need to know the n final and n initial. Well, the n initial is easy. N initial is n equals 6. No problem there. It tells us it starts at n equals 6. Now to find the end final, we have to look at the different hydrogen atom transitions. It says it emits a photon in the IR region. So IR region is the Paschen series, and all of the Paschen series end up at n equal 3. So that's our final energy level. So now we know the final energy level, we know the initial energy level, we can calculate the change in energy. And since we're going from a higher energy level to a lower energy level, energy should be negative because it's being emitted. Oops. So we put in our energy levels, the final and the initial, we square them. Now we take the difference. This is the energy level of that photon. This is the energy released for that photon. Now it wants us to calculate the wavelength. And so for wavelength, we can just take the absolute value of the energy to calculate the wavelength, because you can't have a negative wavelength. So we take the absolute value of E equals h over nu. Nu is c over lambda. So we get the absolute value of the energy change is equal to hc over lambda. Lambda equals hc divided by the absolute value of delta E. Again, since delta E is negative, we can take the absolute value to determine the wavelength, because you can't have negative wavelength. So we plug it in. We calculate the wavelength in meters. Oops, that looks bad. We calculate it in meters, and then we convert it to angstrom. So it's 1.092 times 10 to the negative 6 meters, and we get 10 to the 4th angstroms. Remember, 1 meter equals 10 to the 10th angstroms. So you multiply 10 to the negative 6 by 10 to the 10th, you get 10 to the 4th. Give you a few minutes or a few seconds to look over this before we continue. This is a different type of question. Here we want to know which transition would emit a photon with the longest wavelength. So what we have to remember is our different hydrogen atom transitions. So Bohrs series ends in 2 is the visible part of the spectrum. Lyman series ends in n equal 1 is in the UV spectrum. And then the Paschen series ends in n equal 3 is the IR. So the first thing we need to do is determine which one of these series has the longest wavelength. And the one with the longest wavelength is Paschen, because IR is longer than visible in UV. So the first thing we want to do is omit any ones that don't end in n equal 3. So any ones that don't end in n equal 3, we're going to omit them. So we can omit number or B, which is n equal 2, for C, which is n equal 1, and E. So we can get rid of those 3 because they don't end in n equal 3. Now we're looking for the one with the longest wavelength. So the second thing we do, determine which one has the smallest difference in energy levels. So which one has the smallest difference in energy levels? Well, here n equal 5 minus 3 is 2. 6 minus 3 is 3. So the one with the smallest change in energy level would be D. So D would have the longest wavelength out of all these transitions given. Again, the first thing we do, since we're looking for longest wavelength, is determine which one of the series has the longest wavelength that was passed Chen. So we get rid of all the other transitions that are not passed Chen. The second thing we do is determine which transition has the smallest difference in energy levels, and that was D, which has a difference of 2. So here we want to know what's the final energy level of Bohrs series. So what energy level does Bohrs series end in? And that would be n equal 2. All Bohrs series transitions end in n equal 2. One last example. Here we want to know which of the following electronic transitions would release a photon of energy. So the release of photon of energy start from a high energy level. To release a photon of energy, the initial energy level is greater than the final energy level. So if the initial energy level is greater than the final energy level, you'll release a photon of energy. So let's check. So is N3, is 3 greater than 6? No. So that wouldn't be 1. Is 2 greater than 1? Yes. Is 1 greater than 3? No. 2 greater than 7? No. 4 greater than 2? Yes. So the two correct choices would be B and E. Because again, the N initial is greater than N final. Energy will be released. So that concludes the end of Chapter 7, Part 1 lecture, talking about energy and wavelength. The second part of this chapter will involve quantum numbers and talking briefly about wave-particle duality, and that will end Chapter 7 lecture. So I hope you enjoyed the lecture. If you did, make sure to hit the like button or leave a comment. Thank you, and look forward to having you next time.